So this is going to be a mathematical proof of short darts versus long darts being launched out of a flywheeler. So, to start, we can start with our physics motions equations. Distance equals initial velocity times time plus 1/2 acceleration times time squared. D equals v0 t plus 1/2 at squared. Force equals mass times acceleration. So we can then extrapolate from that is if you divide through by mass, acceleration equals force over mass. We can plug that into here. And then the other thing we can do is when it comes to force, that is going to be rho, the density of air, v naught squared, velocity, times the surface area of incident all over 2, because it's 1/2 rho v naught squared a. And then we multiply through by m, or divide through by m. And then we can plug this whole thing into here. So then you have d equals v0t plus rho v naught squared a over 4m, because you're taking the half and putting that onto this 2. So then next what we can do is we can start plugging in our values. And we also need to multiply that by t squared. So t travel time is going to be about 3 seconds, short or long dart, to keep it consistent. So then rho is constant, which is 1.225, whatever units that's in. V naught. Using the same flywheel setup, we determined that V naught of long darts is 25.5 meters per second, and V naught of short darts is 22.5 meters per second, 75 and 85 feet per second. And then the last thing we need is area. So area of long darts is going to be 7.2, that's the surface area of the dart against on a flat surface, cosine theta, the angle relative to the horizontal. Area of a short dart is 3.6 cosine theta. Mass of a long dart, we're going to say is 3 grams to be easy. Mass of a short dart is going to be 1 gram, which is about average. So the next thing we can do is start plugging in our values and set the equations equal to each other. We don't actually need to find d, because that's very loosely defined in this case. So what we can do is we take v0lt plus rho v naught l squared al over 4ml t squared equals, that's going to equal here, we're going to say v naught s plus rho v naught s squared as over 4ms. So now we can start plugging in our values. So to do that, we will take our original equation. So for L, we have 25.5 times 3 plus 1.225 density of air plus 25.5 squared plus 7.2 cosine theta all over 12, which is 4 times the 30 grams. And then that is going to be equal to your 22.5 times 3 plus 1.225, that should be a times, apologies, times 22.5 squared times 3.6 cosine theta all over 4, since m is 1 in this case. So these equations need to equal each other. So we can start doing multiplication. So that is going to be 76.5, and that's going to be 67.5. So then what we can do, separate these equations out. So 76.5 plus that whole equation is going to then equal, let's see here, just plugging it into a calculator, it appears it'll be 4,000 301.4 cosine theta. And that is going to equal this 67.5 plus 5,023 cosine theta. So then what we can do is start doing our balancing of equations. So these two combined, you're going to get 9 plus 4301.4 cosine theta equals 5,023 cosine theta. You subtract this from both sides. Since it's a term, we cannot divide it. That gives you 9 equals 721.6 cosine theta. Divide through by 9, cosine theta equals very small number, which then means theta equals 89.2 degrees, which corresponds to a 0.8 degree angle above the horizontal. So, with that information, we can conclude that as long as your angle above the horizontal is above, theta is greater than 0.8 degrees, distance of a short dart is going to be greater than distance of a long dart, dl. And that is because despite, this is all in flywheels, despite the fact that your long dart is about 10, you have 85 FPS long and 75 FPS short, but the air resistance makes it so that as long as you have basically any angle above the horizontal, because if they're perfectly horizontal, your area of incidence is identical because it's just the head of the dart. However, you introduce even a slight angle, you can do it like that, and say, so you have one arrow coming this way, one arrow going that way. So if this is at an angle and that's our arrow, you see that the area of incidence with the long dart is much greater than the short dart, despite the fact the long dart is going faster. So what does this mean when using flywheels? 1. Long darts will launch faster than short darts at the initial velocity. 2. Long darts have more drag at any angle above the horizontal, so they will have more drag and slow down faster. Verdict: short darts will fly farther.